Okay, let's see. Number 16. The bronze objects with no instructions. A bronze object lies half buried in a Lincolnshire pit, still carrying the weight of 17 centuries. It is small enough to fit in both hands, yet strange enough to stop an excavation cold. 12 pentagonal faces, circular holes of different sizes, tiny knobs at the corners. The shape feels purposeful, the meaning does not. Around it lie Roman pottery shards, building debris, and the quiet evidence of a villa landscape near the Fosse Way. For the archaeologists, this was not just another find. It was one of the rare dodecahedra recovered in secure context, almost undamaged, as if the ground had been waiting to keep its secret a little longer. We can measure the alloy, map the spread, count the faces, and still not answer the simplest question. What did Romans actually do with it? And what are we seeing when we call it a tool, a ritual object, or a mystery? In June 2023, at Potter Hill near Norton Disney in Lincolnshire, Richard Watts lifted the object from Trench 4 and found that it was not a fragment, not a replica, not a curiosity in pieces. It was complete, 8 centimeters high, 8.6 centimeters wide, 254 grams of copper alloy, with the clean geometry of something made on purpose and the silence of something never explained. The report places it in a pit or quarry filled beside Roman debris, near a villa site, and not far from a road that tied the province together. The scene is ordinary, the object is not. It is the tool Rome forgot to name. That uncertainty is older than the find itself. On the 28th of June 1739, George North stood before the Society of Antiquaries and showed them a 12-sided bronze object from Aston, Hertfordshire. That was the first recorded dodecahedron notice, and even then nobody could say what it was for. Nearly 3 centuries later, the catalogue is larger, about 134 examples in recent counts, with some public summaries still saying 120 to 130, but the answer has not gotten any clearer. More objects, more measurements, more maps, and still no sentence in any surviving Roman text that says, plainly, what one of these things was supposed to do. The form itself looks almost too exact for guesswork. 12 pentagonal faces, 12 holes, 20 corner knobs. Most examples sit somewhere between 5 and 11 centimeters across, about the size of an adult fist, but they are not standardized the way a measuring device should be. That matters, because if you want a practical instrument, you usually want the same dimensions every time. Instead, the Norton Disney piece sits within the known range, but not at some fixed Roman standard. It was cast well. It was not mass-produced. It was expensive bronze, shaped into a form whose purpose still slips away the moment someone tries to pin it down. And the proposals keep colliding with the same hard edge. If it was a measuring device, the different hole sizes might fit rods, gauges, or sighting uses. But then why the lack of standardization? And why do examples appear in so many different contexts with no clear wear pattern? If it was a candlestick, a gaming object, or a craft tool, then why the symmetrical layout, the hollow body, and the recurring knobs at the corners? If it was ritual, then why do they show up in settlements, graves, hoards, pits, rivers, and military sites scattered across Britain, Gaul, the Germanias, and adjacent northern provinces, but not securely in Italy, Spain, Africa, or the Mediterranean summaries we have? Every explanation catches one feature and loses another. The Norton Disney context makes that tension sharper, not softer. The dodecahedron came from a pit fill, not a temple floor, and nearby archaeology has already turned up a mounted deity figure, the Norton Disney rider god. That leans ritual without proving it, which is exactly the trap. Sacred objects can be hidden, deposited, buried, and broken. Practical objects can be lost, discarded, and dumped. The ground remembers the act, but not always the reason. So the question is not simply whether Romans believed in it or used it. It is why one bronze form could move so easily between functions in modern imagination, while leaving no trace of its original one. By the time the object reached modern study, the mystery had already hardened into categories. Scientific analysis can now say the Norton Disney example is roughly 75% copper, 7% tin, and 18% lead. It can say the casting quality is high. It can say the distribution is strangely concentrated in northwestern Europe. But none of that tells us whether the original owner held it as a measuring frame, a ceremonial object, a workshop aid, or something no surviving label ever preserved. The bronze is real. The explanations are not enough. The more each theory tries to cover the faces, the more one hole stays open. Number 15. The crystal that might be nothing. The ancient lens may have fooled us first. In the early 1850s, Austin Henry Layard was clearing the Northwest Palace at Nimrud, the Neo-Assyrian royal complex on the Tigris in what is now Iraq. In room AB, among the ruins of luxury fittings, he found a small, oval piece of polished rock crystal. It was only 4.20 centimeters long and 3.45 centimeters wide. Its thickness ranged from 4.10 to 6.20 millimeters. It was not lying with an astronomer's tools. It was sitting among fragments of blue, opaque glass, likely the broken facing of an ivory or wooden object. The first mystery is not what the crystal could do. It is why it was there at all. Layard did not excavate a scientific instrument. He recovered something that looked like furniture, or inlay, or ornament. Back in Britain, the crystal took on a different life. Sir David Brewster, one of the era's leading optical scientists, examined it and saw a possible lens. Not a modern lens, not a precision glass element, but something that could gather light, magnify crudely, maybe even serve as part of an optical device from the 8th century BC. The object soon became known as the Nimrud Lens. A decorative shard had turned into a candidate for ancient science. The trouble begins with the surface itself. In 1913, John Finn argued in Nature that the crystal's cloudy internal streaks and irregular facets made it a doubtful instrument for serious use. The British Museum still keeps both possibilities alive, because each fits part of the evidence. The object does have optical properties. It can magnify modestly. But the excavation context points elsewhere, toward a decorative composite object rather than a purpose-built tool. The question becomes sharper here. Was the crystal shaped for vision or for beauty? If someone ground it because they wanted to see through it, then the lens was a deliberate act in the Neo-Assyrian world. If it became lens-like because a craftsman polished an inlay hard enough, then what looks like invention may be an accident. The difference sounds small, but it is not. One reading means deliberate optical design. The other means a piece of furniture happened to cross the threshold into magnification. The physical numbers invite both readings. A crystal this size can bend light. A plane surface with a focal length of about 12 centimeters can produce a crude, enlarged image. That is enough to tempt modern eyes. But the same object is uneven, cloudy, and imperfectly finished. Those flaws weaken the case for a tool meant to help with fine work. In a display case, it can look more decisive than it did in the ground. Once the polished face is separated from the palace debris around it, the story starts to drift. Because the crystal does something real, the mind pushes toward a larger claim than the evidence can carry. Ancient people could polish quartz. That is not the puzzle. They could also make beautiful inlays, fit them into furniture, and use the sparkle of stone and glass to project power through luxury. Intent remains unresolved, and archaeology finds surfaces more easily than motives. So the Nimrud piece stays in a narrow, uncomfortable space. It is old enough to suggest possibility, clear enough to measure, and ambiguous enough to resist a clean verdict. Layard's fine context points one way. Its optical behavior points another. The object magnifies a little. It does not prove a lost science. It may be a lens. It may be decoration. In the museum record, it is still only a few centimeters of crystal, and no label can say which one it was. Number 14. The printed message nobody can read. In his excavation report for July 3, 1908, Luigi Pernier recorded a small fired clay disc lifted from dark earth in room 8 of building 101 at Phaistos on Crete. Not from a throne room or a ceremonial court, from a cramped chamber in the northeast complex, more storeroom than palace theater, cut down toward the bedrock. About 55 centimeters above the rocky bottom, in soil mixed with ash, charcoal, and broken pottery, the disc appeared tilted, with the face bearing a central rosette turned upward. A few centimeters away lay a fragmentary linear A tablet, now called PH1. The object was small enough to fit in two hands, about 16 centimeters across. The first shock was the writing. Across both faces, signs run inward in a spiral. There are 242 impressions in all, 123 on one side and 119 on the other. They come from 45 distinct symbols and are divided into groups as if they might be words. But they were not scratched in with a stylus, like ordinary clay texts from the Bronze Age. They were pressed into wet clay with preformed stamps. Then the clay was fired hard enough to survive for more than 3 millennia. So the question comes quickly. Was this a one-off ritual object, made for one ceremony and never repeated? Or was it evidence that Minoan Crete once had a broader writing technology built around reusable sign tools? That distinction matters if you are trying to separate lost genius from modern myth. The technique is right there on the surface. The system behind it is almost completely missing. Pernier's own testimony does not give us a perfect sealed scene. The room had already seen earlier excavation activity, and the layer was not a clean, untouched floor with objects lying where they fell in a single instant. It was a mixed deposit. That does not make the disc fake. It does strip away the easy fantasy of a flawless time capsule. Even the date comes as a range, not a verdict. Most scholars keep it in the Minoan Bronze Age, perhaps around the 17th century BCE, perhaps more broadly between 1850 and 1600 BCE. The nearby Linear A tablet helps, but only up to a point. It places the disc inside a literate world. It does not prove the disc uses the same script, the same language, or the same purpose. Near each other is not the same as identical. You can still follow the maker's hand through the surface. One sign is pressed, then another, then another. The line curves inward in a controlled spiral on one face, then continues on the other. People sometimes call this ancient printing. That pushes the claim too far. There was no press, no rolling plate. What we can actually see is narrower and stranger. Individual stamps, one by one, making repeated signs in soft clay. If 45 symbols recur, then a sign set probably once existed as physical tools. Yet after more than a century of Cretan archaeology, no matching stamp kit has appeared. The disc survived better than its language. Modern testimony sharpens the irony. Unicode gives the signs a place on the digital map, from U+101D0 to U+101FF, and refuses to guess what they mean. Computers can display them cleanly. Databases can count them. Scholars can test frequencies, repetitions, openings, endings. But every proposed decipherment hits the same wall. There is only one known example of this exact symbol system. That sounds minor. It is not. A script usually yields through company, another tablet, a longer text, a bilingual inscription, a scribal exercise, a repeated name you can anchor to a king or a place. Here there is none of that. If one group of signs repeats, you do not know whether it is a title, a verb, a village, a deity, a refrain, or a mistake. Over the last century, people have heard hymns, calendars, inventories, games, charms, and migration records in the disc. The object is short enough and alone enough to tolerate almost any theory. So we return to the opening split. A one-off ritual object would look isolated. A broader writing technology could also look isolated if every other example is gone. The disc cannot choose between those stories. A single isolated text cannot unlock itself. A second stamped text from Crete might change the case in a day. 10 shared signs on a clay fragment might be enough to start eliminating whole families of guesses. A box of the original stamps would tell us even more. None of those witnesses has turned up. In the Heraklion Museum, the fired clay still holds 242 impressions. The spiral narrows toward the rosette. The only exact example of the script is still the one Pernier lifted from room 8 on the evening of July 3, 1908. Number 13. The perfect shapes in the jungle. In the Dakis Delta, a stone sphere sits on trimmed grass with a museum label nearby. It looks inevitable there, as if it always belonged beside a path under open sky, ready for photographs. Many of these spheres did not survive in places like that. They survived because they were buried. The moment they were exposed, people began dragging them away. The monuments whose secret may have been moved out of place. In 1948, Samuel K. Lothrop walked the banana lands of southern Costa Rica with a notebook, a tape measure, and a problem already slipping out of his hands. Drainage work had cut into the floodplain. Plantation clearing had exposed stone after stone. Some were half buried in ancient sediment. Some stood near mounds. Some appeared in lines. Others had already been rolled, hauled, or relocated to house yards and company grounds. A perfect stone ball in a field does not look like evidence at first. It looks like an obstacle. That shift in position may have erased the message itself. The public had heard of Costa Rica's stone spheres as early as 1886. The landscape opened in a much harsher way in the 1930s, when banana company drainage and plantation work cut into the Diquís Delta. In 1939, Conchita Turnbull and Jorge Lines made an early expedition into the region. In 1943, Doris Stone published the first scientific article. She described spheres at 5 sites and linked them to mounds and possible ceremonial use. She was not writing about one eccentric object. She was documenting a pattern emerging from the ground. The spheres belonged to pre-Columbian chiefdom societies, active roughly from 500 to 1500 CE. They were appearing where power had once been staged in earth, stone, and carefully ordered space. Then the count kept growing. Around 300 spheres are now registered by the National Museum of Costa Rica, most of them in the Diquís region. Not one marvel, not one stray sculpture, hundreds. UNESCO's protected examples range up to 2.57 meters in diameter. The largest sphere recorded at El Silencio reaches about 2.66 meters and roughly 24 tons. This was not something one family could casually shape on the side. It required repeated quarrying, repeated transport, repeated finishing, repeated placement across an entire cultural landscape. The finish still unsettles people. These are not rough boulders that only seem round from a distance. Some are strikingly regular. Stoneworkers seem to have shaped them from granodiorite and other hard rocks, likely using hammerstones, controlled pecking, and grinding. No metal tools, no surviving workshop manual, just mass, geometry, and labor. The old temptation appears immediately. If the forms look too perfect, the story must be mythical. But the stronger the archaeology gets, the less room there is for fantasy. The gap that remains is sharper and more stubborn. Humans made them. The harder question is how they organized the work, and why so much effort went into a shape that had to mean more than decoration. Some spheres were not alone. At sites in the Diquís region, archaeologists found them associated with mounds, plazas, ramps, and settlement features tied to ranked societies. These were not random ornaments dropped into the jungle. They marked authority. They signaled hierarchy. They may have framed ritual movement through space. Finca 6 matters especially because it is the only site that still preserves spheres in linear arrangements. That detail changes the reading entirely. A single sphere can support almost any story. A row cannot. A row implies planning, sightlines, approach, maybe procession, maybe status announced before a word was spoken. Movement is exactly what destroys that. Roll a sphere 20 meters or 100, load it onto a truck and set it beside an office lawn. Its diameter survives, its weight survives, even its beauty survives. What disappears is context, the angle to a ramp, the distance to a mound, the spacing to the next stone, the fact that one group faced a settlement entrance while another marked a terrace edge. Archaeology can recover objects. It is much worse at recovering choreography after the floor plan has been kicked apart. The buried ones mattered because sediment protected more than stone. Thick layers sealed many spheres for centuries. They also sealed the arrangements that could explain them. By the time systematic recording began, much of that wider setting had already been damaged by looting, clearing, and relocation. Lothrop's maps became a baseline. Later researchers needed proof that some of these stones had once stood in meaningful positions, not just scattered where modern eyes found them. In 2014, UNESCO finally inscribed 4 sites, Finca 6, Batambal, El Silencio, and Grijalba II, as a World Heritage Property. What survived was not merely a collection of impressive objects, it was the remains of a designed landscape. One practical problem sits under all of it. A 24-ton stone does not move itself out of the coastal range foothills. It has to be quarried, reduced, shaped, moved downslope, brought across difficult ground, and then finished or refined into a near-spherical form. Maybe that meant rollers, maybe ropes, maybe earthen ramps and coordinated labor under chiefly control. Each proposal works in pieces. The full chain is still frustratingly incomplete. We have the stones, we have the chiefdoms, we have the sites. We do not have the transport system preserved in the ground as clearly as the finished result. That leaves the central split in the larger question very much alive. Lost genius would mean a real technical tradition hidden behind a deceptively simple shape. Modern myth would mean people filling silence with aliens because round stones feel unnatural in a jungle. The scientific gap is narrower than either of those stories. It is also more irritating. The spheres may have been understandable all along. Political markers, ritual architecture, engineered symbols of power, and the clearest evidence may have been sitting in their placement. Then the spheres were moved. At Finca 6, a few still hold their lines. Elsewhere, the stone remained, but the layout did not. A worker sees a half-buried sphere in a wet field, hooks a chain to it, and drags it clear. Number 12. The underground room that changes voices. In 1902, on a hill in Paola, Malta, a stonemason was digging house foundations when his tool broke through limestone into a space that should not have been there. Not a cave, not a storage pit, a 3-level underground complex, cut deep into soft rock, and used from around 4000 BC to 2500 BC, with the remains of roughly 7,000 people spread through its chambers. By the end of 1903, the site had become public property, and digging continued until 1911. What emerged was the Hal Saflieni Hypogeum. The middle level is where the dispute never settled. That level contains the oracle room. A small carved niche in the wall throws a voice back in a way that catches you before the words are finished. Speak low, and the room answers. Speak deeper, and the chamber seems to catch the sound and hold it in place. UNESCO describes the Hypogeum as a subterranean counterpart to the megalithic temples above ground, with false bays, door-like openings, windows, and corbelled ceilings copied into the stone. This is not just an empty void. It is underground architecture, made to feel like a building that should have been standing in daylight. The room has resonance. That part is not in dispute. The dispute is over why it has it. Accident or design. A later acoustic study found a double resonance at 70 Hz and 114 Hz, frequencies that line up with the lower range of a male voice. Another paper in 2020 argued that the chamber geometry itself looks deliberately tuned. The oracle room is also one of the only prehistoric painted interiors on Malta. Red spirals and honeycomb-like motifs share the same ritual space as the acoustic niche. Sound and image occupy the same chamber. Down there, the effect feels personal. The chamber is narrow, dark, and close enough that your own voice seems to come back wearing someone else's shape. There are no crowd noises, no wide-open hall, no obvious natural feature you can point to and use as an easy answer. Heritage Malta treats the site as a fragile conservation case, not a spectacle. Light is controlled, humidity is controlled. Visitor numbers are controlled down to 10 people per tour. The place is so delicate that the modern world can only enter in small pieces. That suits a chamber whose strongest feature is the way it breaks sound apart and sends it back. Preservation is one thing, intention is another. Acoustic measurements can prove that the niche and the chamber geometry produce specific resonance effects. They can show that the room amplifies and colors certain tones. They can make a strong case that ancient builders understood how it behaved. What they cannot prove on their own is the exact purpose in the minds of the people who cut it. Ritual use leaves traces. Knowledge of voice, echo, and sensation leaves traces. Intent, unless it is written down, is harder to recover. So the room remains suspended between engineering and meaning. The physical effect can still be measured. The reason for building it is gone. That is what keeps drawing researchers back to the Hypogeum. It belongs to a world old enough to leave almost no explanation behind, yet precise enough to suggest that someone was paying very close attention. You can measure the 70 Hz. You can measure the 114 Hz. You can map the chamber. You can model the reflections. What you cannot do is stand in the oracle room and state, with certainty, what its builders meant. The chamber still answers. The reason it was taught to answer does not. Number 11. The jar that became a battery. In 2005, 10 clay jars on a television workbench produced about 4.5 volts from lemon juice. Not much. Enough to make the claim hard to ignore. If a row of replicas can push a measurable current today, did someone near ancient Baghdad build the same thing on purpose nearly 2,000 years ago? In 1936, at Kujut Rabu outside Baghdad, excavators uncovered a set of small, unglazed ceramic vessels. Inside each sat a copper cylinder sealed with bitumen, with an iron rod running down the center. The parts look almost too neat. Clay outside, copper and iron inside. Seal it up, add an acidic liquid, and modern chemistry starts nodding immediately. Between the 3rd century BCE and the 3rd century CE, somewhere in that Partho-Sasanian window, these jars entered the ground. By themselves, they were odd. In the trench, they were not famous yet. They became famous 2 years later, in 1938, in a museum. Wilhelm Koenig of the Iraq National Museum looked at the fragments and made the leap that gave the object its afterlife. Perhaps this was not a ritual container. Perhaps it was a galvanic cell. Copper and iron, separated and suspended in the right liquid, can produce a weak electrical current. Suddenly the jar had a modern identity. Not incense, not scrolls, a battery. That idea spread because it is easy to test. Build the thing again. Fill it with something acidic. Measure what happens. Later reconstructions did exactly that and got small voltages, often around 0.8 to 2 volts per vessel. Low, but real. Then television arrived and made the image stick. 10 replicas wired in series. Lemon juice as the electrolyte. About 4.5 volts on the meter. Ancient electricity, apparently humming away on a modern bench. The object works better as a question than an answer. A device that can make electricity is not automatically a device that was made to make electricity. That distinction sounds fussy until you try to prove it. You need more than a current. You need intent. You need the rest of the system, a wire, a terminal you can actually use, a thing being powered, a workshop, a text. Something showing that ancient craftspeople understood this jar not just as a container with reactive metals inside, but as part of a practical electrical setup. What survives does not give you that chain. Archaeologist William B. Hafford has argued that Koenig was working from reconstructed fragments, not from an intact object sitting safely in a secure, well-recorded context. That matters because context is where archaeology stops being clever and starts being reliable. A loose cluster of parts can invite modern imagination to do the assembly for you. The word battery enters the story, and every bit of corrosion starts to look like confirmation. But the physical object keeps pulling people back. Copper cylinder, iron rod, bitumen seal. It is almost rude in how well it imitates a simple electrochemical cell. Some later proposals even tried refining the design further. In 2026, Alexander Bazes suggested a 2-cells-in-1 model that could produce around 1.4 volts per unit. The engineering games never really stop, because the geometry keeps offering just enough plausibility to stay alive. So the fight here is not chemistry. Chemistry is the easy part. The fight is overuse. One suggestion is electroplating. A weak current could, in theory, help deposit metal onto another object. It sounds exactly like the kind of lost practical trick people love. Ancient artisans with a secret process, half workshop skill and half accidental science. But no confirmed set of artifacts requires that explanation, and no secure ancient setup has turned up beside the jars to show plating in progress. No clipped leads, no conductive bath, no bench covered in tools that only make sense if the jar was feeding current into something else. Hafford's alternative is stranger in a different direction, and maybe more faithful to the world these objects came from. The vessels may have been ritual containers, perhaps sealed with prayers or incantations and buried in foundations. In that reading, the copper, iron, bitumen, and sealed interior are not failed engineering clues. They are the technology of ritual, a device for trapping, directing, or symbolically containing unseen forces. Not electrical in the modern sense, but not meaningless either. If ancient people really built things we still struggle to explain, how do we separate lost genius from a myth made of familiar parts? Here, the jar sits exactly on that line. It can do the modern trick. It may never have been meant to. Then the evidence got thinner. Between April 7th and April 12th, 2003, during the looting of the Iraq Museum, roughly 15,000 items were stolen. About 5,000 cylinder seals disappeared among them. Many original Baghdad Battery pieces vanished too. What remained were photographs, notes, replicas, and arguments. The objects that might have settled details of construction, wear, residue, or context were suddenly absent from the table. So the official label survived, the Baghdad Battery, but the actual case never caught up to the name. The jars can be rebuilt, they can be filled, they can produce a tiny current. What still does not exist is the missing chain behind the claim. No wires, no powered device, no text describing electrical use, no intact workshop context, and in many cases, no original object left to inspect. Number 10. The Roman glass with two colors. In late Roman hands, a drinking cup could do something that looked less like decoration and more like a dare. Hold it one way, and it was green. Let light pass through it, and it turned deep red, as if the glass itself had changed its mind. The cup turns light into a confession. The object is the Lycurgus Cup, a 4th century AD luxury vessel, about 158.8 millimeters high, 132 millimeters across at its widest point, and weighing roughly 700 grams. It shows King Lycurgus trapped in vines, while Dionysus and his followers close in around him. The scene is violent, theatrical, and strangely fitting, because the cup does not just depict transformation, it performs it. By the mid-19th century, the cup had entered the Rothschild collection, and in 1850, it was on display in London. In 1958, the British Museum bought it from Victor, 3rd Lord Rothschild, and that same year the museum removed a later metal foot. Underneath, the original fragments from the base were still there, loose and overlooked. They became the clue that changed everything. For a long time, people could see the trick but not explain it. It was glass, not jade, not opal, not some impossible mineral from a lost workshop. But why did it behave like this? That question matters because the cup sits right on the edge between accident and control. Was it a luxury experiment that happened to work once? Was it a recipe a workshop could repeat on command? Or was it a narrow technical sweet spot that Roman glassworkers found by trial, then only partly mastered? The answer was waiting inside the material, but it took modern science to pull it out. In the late 1980s, David Barber and Ian Freestone examined a tiny sample with analytical transmission electron microscopy. In 1990, they showed the effect was real physics. The glass contained tiny particles of gold and silver, alloyed together and measuring only tens of nanometers across. Those particles scattered and transmitted light differently, so the same cup could appear green in reflected light and red in transmitted light. The surface was not painted. The color was built into the glass at a scale Roman eyes could never directly see. Later analysis sharpened the picture even more. The particles are typically around 50 to 100 nanometers in diameter, with a silver-gold ratio of roughly 7:3 and about 10% copper mixed in. That is not decorative contamination. That is a structured material, tuned to change how light moves through it. And the object itself belongs to an unusually rare class. Only about 50 to 100 Roman cage cups are known, which makes this one not just elaborate, but exceptional. The hardest part never disappeared. Knowing what the cup is made of is not the same as knowing how Roman makers achieved it. Particle size, distribution, and firing conditions all had to land inside a very narrow range. Too large, too uneven, too hot, too cold, and the effect would fail. The glass gives up its secret at the microscopic level, but the workshop process stays stubbornly out of reach. We can read the physics. We still cannot fully reconstruct the hand that controlled it. The Lycurgus Cup is unsettling because it is not a myth pretending to be science. It is science hiding inside a myth. A royal body caught in vines. A vessel that changes color when the light changes. A Roman luxury object that proves ancient makers had access to a kind of nanotechnology long before anyone had the language for it. The cup has already confessed what it is made from. The only thing still missing is the exact Roman recipe, and the firing table that turned metal dust into this red, green, impossible cup. Number 9. The iron that refused to rust. In the courtyard of the Quwwatul Islam Mosque at Merouli, the year is already doing something strange to the metal. The iron pillar of Delhi stands 7.02 meters from base to bell capital, with 0.93 meters buried below ground, and weighs about 6 tons. It is ancient, public, and measurable. A 4th century Sanskrit inscription names a ruler called Chandra, usually identified with Chandragupta II, who ruled around 375 to 413 CE. Yet people kept calling the pillar rustless, as if the metal had escaped the rules that govern every other iron object on Earth. That is the first clue, not that it never changed. It changed in a very specific way. By the late 20th century, scientists were no longer asking whether it rusted. They were asking why it did not fail in the normal way. Why did this iron form a protective film instead of ordinary rust? The pillar is not hidden in a dry museum case. It has stood in open air, through Delhi's alternating wet and dry seasons, long enough for weather to become part of the evidence. In 1997, the Archaeological Survey of India installed a grill cage around it to stop visitors from damaging the surface, and researchers noticed something almost clinical. A brighter patch near chest height, once exposed to handling, slowly darkened over time. The monument was not just surviving, it was recording its own environment. The old fascination with the pillar always began with the surface. From a normal angle, the iron can look black, but catch it at the right angle and a golden hue appears, as if the skin is reflecting light through something thinner than rust and harder than paint. That is not magic. It is chemistry. Studies point to phosphorus-rich wrought iron, slag inclusions, forge welding, and a passive layer rich in phosphates that forms on the surface and slows corrosion. The average composition often cited is about 0.15% carbon, 0.25% phosphorus, with sulfur and manganese extremely low, and only traces of silicon, nitrogen, copper, and nickel. Small numbers, outsized consequences. The question is, why that chemistry works so well here? The answer seems to live in a combination of metal and climate. High phosphorus can help build a thin, adherent protective film. Slag inclusions can change the way moisture and corrosion products move through the iron. Delhi's wet-dry cycling helps that film stabilize instead of constantly drowning it. The exact weight of each factor is still debated, especially because the monument cannot be freely sampled the way a laboratory specimen can. The oldest corrosion studied came from an area the public cannot normally reach, just below the decorative bell capital. That hidden patch became a test site for a material puzzle that no one could solve by simply cutting the pillar open. The evidence standard rises. This is not a rumor carved onto a lost fragment. It is a standing object with a date, a ruler's name, a known location, and visible change tracked over time. UNESCO records also note that the pillar was brought from elsewhere in India before ending up in the Qutb complex, where the mosque itself began in 1192 and was enlarged between 1211 and 1236. That history matters because the pillar's story is not just about making iron. It is about moving it, preserving it, and leaving it in a place where centuries of air could keep testing it. The science becomes harder, not easier, because the object is still there, still accessible, still refusing to fit the simplest expectation. The pillar's survival is impressive not because science cannot explain it, but because it took so long to pin down why it works. The iron is ordinary enough in bulk, yet unusual in composition. The environment is ordinary enough in weather, yet powerful in repetition. Put them together, and a passive layer forms that shields the metal instead of feeding the rust. Whether that outcome was intentional is still not fully settled. Did ancient smiths know exactly what they were doing, or did a set of practical choices accidentally produce an answer that would not be recognized for more than 1,000 years? The monument keeps its silence. The skin is the armor. Under that dark surface, the chemistry still looks like a clue, waiting for the last line of testimony. Number 8. The dragon jar that heard distant quakes. When the iron pillar of Delhi survives, it does so because the surface itself changes the rules. The next mystery is not a statue that resists decay, but a device that seemed to feel events no one could yet see. In 132 CE, at the Eastern Han court in Luoyang, Zhang Heng stood before the emperor with a bronze vessel that looked like a ritual urn, crowned with 8 dragon heads and ringed with 8 toads. He was not claiming sorcery. He was trying to build a machine that could register an earthquake mechanically, long before anyone in the room felt the ground move. Zhang Heng was a Han Dynasty polymath, born in 78 CE, and by the time he presented this strange bronze object, he had already earned a reputation for mathematics, astronomy, and engineering. This was different. It was an answer to a problem no one had solved. The court saw a polished vessel with animals fixed around its sides. What they could not see was the mechanism inside, because the original is gone. Later descriptions suggest a suspended mass or hidden pendulum waiting in the dark center of the urn. When seismic motion shook the frame, that internal weight would shift, trip a latch, and release a bronze ball from one dragon's mouth into the toad below. One direction, one impact, one silent report from a place the court could not yet name. The machine stayed quiet in Luoyang, where no one felt a quake at all. The skeptics mocked it. A bronze jar that did nothing. A court display. A clever ornament with a good story attached. Then a messenger arrived from the west, with news of an earthquake in Longxi, in modern Gansu, roughly 400 to 500 kilometers away. The direction matched the dragon that had fallen. The room had missed the tremor, but the vessel had not. The machine that reported a disaster before the witnesses arrived was not a prophecy. It was a question in bronze. That question has a name now, the Zhang Heng seismoscope. The old descriptions place it in 132 CE, though the exact quake it confirmed is still argued over. Some modern textual studies point to December 13th, 134 CE. Others still treat the key event as the 138 CE Jincheng Longxi earthquake. The problem is not that nothing happened. The problem is that the record is thin enough to split into competing histories, and the mechanism itself is lost. That matters because modern reconstructions are all guesses built on a few surviving lines of text. Since 1875, at least 13 different models have been proposed. Some are elegant, some are clearly more conceptual than functional. One reconstruction shown in 1951 even contained a fundamental mistake. In 2002, the China Earthquake Administration and the Bureau of Cultural Relics organized a new study, trying to separate workable engineering from later imagination. Every version reaches into the same empty space. The original interior was never preserved. So what moved first inside the vessel? A pendulum, perhaps, a weighted lever, a trigger hidden in the base. Each reconstruction gives a different answer, and each one changes the story. The bronze dragons and toads are not the hard part. They are the visible theater. The real work is happening where no eye from 132 CE could follow. The surviving accounts make the device sound almost too neat. 8 dragon heads aligned to the principal directions, 8 toads waiting below, a bronze ball dropping when the source was detected. That neatness is exactly why the object still lives between engineering and puzzle. It looks obvious only after you have already accepted the mechanism. Before that, it is just a vessel with animals on it, and a claim that a quake in the west can make metal speak in the capital. Zhang Heng died in 139 CE. The court moved on. The machine did not survive. What survives instead is a description, a set of reconstructions, and a gap that keeps widening every time someone tries to close it. The dragon jar heard the quake. Which machine are we actually looking at when we say it did? Number 7. The star knowledge that became a trap. In October 1946, on the Bandiagara escarpment in what was then French Sudan, Marcel Griaule sat with a Dogon elder named Ogo de Meli and began writing down a cosmos. Not a telescope log, not an instrument manual. A spoken world of ritual language, layered symbols, and explanations given over weeks of conversation in October and November. Out of that chain of notebooks came a claim with striking precision. The Dogon knew Sirius had an unseen companion, and that companion moved in a cycle of about 50 years. The star map may reveal more about us than the sky. That claim sounds impossible, so start with the evidence chain. Ask where it first appears. Sirius B is real. Friedrich Bessel inferred a dark companion in 1844 from the wobble of Sirius itself. In 1862, Alvin G. Clark and his father finally saw it. Modern astronomy gives its orbital period as about 50.13 years. Those numbers are solid. The puzzle is whether they belong to an old Dogon tradition before outsiders arrived, or entered the story later through collection, translation, and retelling. From 1946 to 1950, Griaule and Germain Dieterlen conducted the central Dogon inquiry in the Bandiagara Circle. In 1950, they published a paper whose title already showed where the focus had landed. Un système soudanais de Sirius, a Sudanese system of Sirius. What later readers pictured as a star map was not a carved chart or an ancient diagram. It was an ethnographic reconstruction built from oral testimony, ritual terms, and interpretation. Griaule's paper did not even present the Sirius material as uniquely Dogon. It said comparable elements also appeared among the Bambara, Bozo, and Minyanka. That detail matters, because the popular version usually comes as a clean image. One isolated people, one impossible secret, one ancient diagram pointing to an invisible star. The document underneath is messier, more human, more exposed to the oldest problem in the history of science. Not fraud, exactly. Mediation. One person asks, another answers, a third writes. A fourth translates. By the time the world hears the result, the conversation has hardened into a system. In 1948, Griol published Dieu d'eau. In 1965, the English translation appeared as Conversations with Ogo Temeli, 230 pages that carried Dogon cosmology far beyond French anthropology. The material was vivid and strange. It reached readers at exactly the moment when ancient wisdom could be sold as superior to modern certainty. The story moved again, first from field notes into scholarship, then from scholarship into mass-market mystery. In 1976, Robert Temple pushed it through that final door with The Serious Mystery. The claim was no longer a disputed interpretation of oral material gathered in the late 1940s. It became evidence that ancient people possessed advanced astronomical knowledge, perhaps from a lost civilization, perhaps from something even less earthly. In the retelling, key parts disappeared: the interviews, the translators, the symbolic language, the distance between a ritual narrative and a technical statement. The star map grew sharper each time the original record grew blurrier. Here, the larger question of the video starts to press. If ancient people really built or knew things we still struggle to explain, how do we separate lost genius from modern myth, and both from a real scientific gap? In the Dogon case, the object at the center is already slippery. There is no ancient instrument to test, no inscription listing orbital periods, no metal device with worn teeth and measurable ratios. There is only a reporting chain. What happens when someone tries to walk that chain backward? In 1991, anthropologist Walter Van Beek published a restudy in Current Anthropology, Volume 32, Number 2, pages 139 to 168. He went back to the Dogon and looked for the elaborate Sirius-centered system reported by Griol. He could not reproduce it. Later summaries put the result bluntly: no trace of the detailed Sirius lore, not a damaged trace, not fragments of a 50-year orbital doctrine. No trace of the system as it had entered popular imagination. That does not automatically prove Griol invented it. Fieldwork is not a laboratory replay. Traditions change. Some knowledge is restricted. Some answers depend on which elders are speaking, under what circumstances, and to whom. But the burden of proof changes. The extraordinary part of the story was never Sirius itself. Sirius is easy. Humans have watched Sirius forever. The extraordinary part was the invisible companion and the near-correct cycle. Those details are attached, not to an ancient artifact, but to a 20th century reconstruction that later researchers could not firmly recover. Officially, the Dogon Sirius story is often presented as ancient African star knowledge, too accurate for conventional history. The paper trail says something narrower and stranger. It runs from 1946 interviews to a 1950 paper, to a 1965 translation, to a 1976 bestseller, and then to a 1991 restudy that could not find the same sky at all. The famous star map was not an ancient map waiting in the sand. It was a modern chain of reporting, hardening each time it moved farther from the original voices. Number 6. The steam engine that did not start an industrial revolution. The engine that arrived before the world had a use for it. Around 62 CE, in Roman Alexandria, Heron of Alexandria wrote down a machine that sounds absurdly early. It is a steam device with no piston, no gears, no flywheel, and still, it produces rotation. In Pneumatica, device number 50, the setup is easy to overlook. A sealed cauldron sits over a fire. From its lid, one pipe rises into a hollow metal sphere mounted between two pivots. Two smaller pipes stick out from the sphere at opposite ends of a diameter, bent in opposite directions. Water boils. Steam enters the ball. Steam escapes through the angled nozzles. The sphere begins to spin. It sounds like the first note of the Industrial Revolution. But it stops there. What stands out is the way Heron presents it, not as a prophecy, not as a plan for factories. He places it among devices and effects. Right before the spinning sphere, he describes another steam demonstration, one where a jet supports a light ball. Steam lifts, steam turns. In Heron's surviving works, that sits alongside automata, surveying, mechanics, and artillery. It reads more like a workshop notebook than a blueprint for industry. Heron was not pulling the idea out of nowhere. Much earlier, Vitruvius had described hollow bronze balls with a small opening, partly filled with water and heated before a fire. When the water boiled, he wrote, a strong blast came out. For Vitruvius, the point was natural philosophy. Heat and moisture generate wind. By the time Heron sends steam into a rotating sphere, the pieces already exist. Hot water can create moving vapor. Confining it matters. Directing it matters even more. The physics is simple. Steam jets leave in one direction, so the sphere is pushed in the other. Reaction thrust. The same basic principle shows up later in far more important machines. That is what makes this little device so hard to shake off. Explaining how it worked is easy. Explaining why it did not lead to pumps, mills, mines, or transport is much harder. This is where people start to project fantasies onto it. A steam-powered rotor in the 1st century invites that. But ancient technology only gets interesting when it survives dull questions. What exactly did it do? How much power did it deliver? What else had to exist before that motion could matter? Look at the machine itself. The famous spinning ball resembles an engine, but it is a weak one. Steam travels from the cauldron into the sphere through one pivot, then vents through 2 tiny bent pipes. Yes, that creates motion. It does not create controlled, transmitted work on an industrial scale. Rotation by itself is not usable power. A wheel spinning freely above a flame is a demonstration. A wheel that drives another machine, every day, under load, belongs to a whole economic system. That missing step matters. The ancient world already knew plenty of clever motion. Temple doors opened by heat, water organs played, automated theaters moved, pressure tricks worked behind the scenes. Heron wrote about several of them himself. The aeolipile belongs to that world. People clearly knew how to turn physical principles into mechanisms and spectacle. But that is not the same as rebuilding labor around a machine. Even centuries later, that gap was still there. In the 16th and 17th centuries, thinkers including Descartes used the aeolipile mainly to think about natural winds, not as the ancestor of the locomotive, as a model for air. By around 1590 to 1600, European metalworkers were also making bronze aeolipiles that could serve as steam blowers, intensifying hearth fires and even seeming to spit flame. The object did not vanish. It kept reappearing, just not on the road to factories. It lived on as a physics instrument, a fire tool, a theatrical prop. So the silence around industry is not about forgetting the spinning sphere. People remembered it. The problem is simpler. A spinning sphere was not enough. To turn this small Alexandrian device into an engine that remakes society, almost everything around it would have to change. Fuel would have to be cheap enough to burn in bulk, not for a brief demonstration, but for continuous work. Metallurgy would have to hold pressure with far less loss through leaks and poor fits. There would have to be a reason to replace labor in a world where human and animal muscle were often cheaper than complicated heat machines. And motion would have to be carried outward through shafts, linkages, gearing, and durable moving assemblies into pumps, mills, or carts. Without that whole package, steam does not become industry. It becomes motion looking for a job. Heron never plainly says, "This is only a toy." Later writers often say it for him. Maybe they are right. Maybe they are reading the verdict backward because they know what failed to come next. Heron's text says less and gives less away. It just lays out the sequence. Fire under a cauldron, steam through a tube, a hollow ball between 2 pivots. 2 bent outlets, rotation. That may be the clearest answer. No suppressed revolution, no near miss where Rome almost built Manchester. In 1st century Alexandria, someone described a real steam-driven rotor centuries before steam power could matter. The surrounding world still lacked cheap fuel, precision metallurgy, labor pressure, and the transmission systems that could turn spin into work. So the small sphere hisses through its bent pipes and keeps turning in place. Number 5. The walls with no room for a blade. A tourist guide presses a metal blade toward a seam in the wall above Cusco, and the trick still works. The edge skates over limestone faces and stops at a joint so tight it seems to vanish. No mortar, no straight courses. One stone swells outward, another dips around it. 5 sides here, 8 there. The angles look improvised until they lock. You start asking the practical question almost immediately. What sequence of work produces a wall like this? One contact at a time, across blocks that can stand 9 meters high and weigh well over 90 tons. In the mid-15th century, on the ridge north of Cusco, the Inca ruler Pachacuti began turning an older occupied hill into the monumental complex now called Sacsayhuaman. Later tradition preserved names for the designers: Walpa Rimachi, Marikanchi, Akawana, Kala Kunchui. That matters. This was not a secret miracle that appeared overnight. It was a state project. Labor rotated in by the thousands. Quarrying crews broke stone free. Hauling crews dragged it uphill. Stoneworkers pounded surfaces with hammerstones, set blocks in place, pulled them back out, struck away the high points, and tried again, then again, and again. They kept going until the outer faces met without a visible gap. The shape of the place matters as much as the stones. Sacsayhuaman did not face Cusco in one clean straight line. It dropped in 3 giant zigzag terraces, more than 540 meters of wall, a broken geometry with up to 40 segments per line. From a distance, it looks ceremonial. In May 1536, it became brutally practical. You are on the heights above Spanish-held Cusco. Manco Inca's forces hold the ridge. Below, the city is packed with thatch. Heated stones come down from above. Sling fire drives at anyone trying to climb. Juan Pizarro leads the counterattack, with cavalry and infantry, but horses are almost absurd on ground like this. The terraces kink, the approach is narrow, the defenders own the elevation. 2 assaults fail, the third finally breaks through. Juan Pizarro is mortally wounded. The walls that tourists touch for their impossible precision once worked as battlefield geometry. The famous wall hides the workshop that made it, not because the stones conceal some mystical code, because the process that produced those joints is the very thing the finished wall erases. Once the faces close, you see the result, not the order. You cannot see which stone was dressed first, which edge was left proud and then knocked down. How many times a 20-ton block had to be nudged, lifted, reset, and tested before one corner finally sat flush. The wall keeps its answer by removing the evidence of its own revisions. That gap between the finished fit and the missing workflow is where the larger question becomes useful. If ancient people built things we still struggle to explain, the first question is simple. Is the mystery in the object, or in the vanished chain of labor that made the object ordinary to its builders? In the 1980s, architectural historian Jean-Pierre Pratzin went after that chain like a forensic problem. Start with the toolkit. No steel saws, no machine polish, but pry bars, large hammerstones, small hammerstones, abrasion, leverage, and time. His experiments suggested the impossible fit did not require cutting every polygon as a perfect abstract shape before it reached the wall. The work could be local and iterative. Prepare one face. Set the block against stones already laid. Mark the contact points. Remove it. Pound down the high spots. Put it back. Repeat until the meeting line tightens. What looks like a single act of precision may be accumulated correction. That explanation makes the small seams less supernatural, but it leaves the heavy part untouched. Shaping a block on the ground is one problem. Maneuvering a block of 90, 100, maybe 125 tons into final position on a slope is another entirely. This is not fantasy, it is logistics. Friction, ramps, cribbing, levers, teams, control. The basic toolkit is plausible. The full-scale choreography is where the reconstruction still thins out. Sacsayhuaman adds one more complication. What stands there now is only part of what stood there then. After the conquest, Spaniards stripped much of the site for building stone in Cusco. The smoother, more convenient masonry was carried away and reused. The biggest blocks remained for a practical reason. They were too massive to steal easily. So the monument surviving on the ridge is partly a negative image, the portion colonial builders failed to remove. An archaeological park of roughly 3,000 hectares and 33 sites still spreads across the area, but the wall most people remember is not the complete structure. It is the residue left behind by extraction. So the blade returns to the joint. The missing evidence is not whether Inca masons could make stones meet that tightly. The stones are there. The missing evidence is the construction sequence itself, the ramps, bedding choices, hauling paths, temporary supports, and repeated fitting stages that vanished while the wall remained. The seam survives, the workshop does not. Number 4. The blade recipe that disappeared. In 1904, at Mawalgaha in what was then Ceylon, Ananda Kumaraswamy stood beside a furnace and watched steel being made the old way. not folded show steel, not modern billet patterns pressed and twisted for effect. Crucible steel, small cakes of metal melted, cooled, and carried forward into blades whose watered surface looked almost liquid when the light moved across it. That distinction matters more than the legend. One is a pattern laid onto steel, the other is a metallurgical chain that has to be carried intact from one generation to the next. The sword modern steel can imitate, but not truly remember. Coomaraswamy was an art historian and curator, but here he was simply watching a craft that was disappearing. In Sri Lanka, he was not looking at the famous Damascus blade at the end of the story. He was looking at the beginning, still alive. The feedstock for historical Damascus was often woots, a crucible steel first produced in South India, in present-day Tamil Nadu, by the mid-1st millennium BCE. The ingots were small, often around 2.3 kilograms. The carbon was high, about 1.5%. Those ingots then moved across Asia. In the Islamic Middle East, especially around Damascus, smiths forged them into swords that became legendary for toughness, sharpness, and that unmistakable watered pattern. The name most people remember comes from the finishing city. The recipe came from a route. You can see how early that route spread. The British Museum holds an 88-centimeter sword from Iran, dated to the 6th or 7th century CE, forged from crucible steel. That is centuries before later Romantic stories turned Damascus steel into a near-mythic substance. The technology was already traveling, already changing, already being practiced far from the place that would lend it its most famous name. Ancient smiths made remarkable blades. They did. The harder question is what modern people mean when they claim they have recreated Damascus. Have they revived a lost craft, repeated a myth, or rebuilt only the visible skin of the process? For almost 200 years, metallurgists argued over that. Some focused on forging methods, some on cooling rates. Some chased secret additives, plant materials, or ritual tricks that sound convincing until the microscope arrives. The blade resisted simple answers because there was never just one answer. It began in ore. It passed through crucibles. It froze into ingots. Everything depended on how those ingots were reheated, how far they were forged, and the exact moment the smith stopped before the structure was destroyed. In the 1990s, in Iowa, of all places, John Verhoeven, Alfred Pendray, and William Docksch pushed closer than almost anyone before them. They were not chasing folklore. They matched chemistry, heat treatment, and mechanical practice to the evidence from museum blades. The picture sharpened fast. Very small impurities mattered. Around 40 parts per million of vanadium could help produce the banding. The forging window mattered. The thermal history mattered. In their experiments, 6 to 8 carefully controlled thermal cycles could bring the carbide bands into clear view. It sounds technical because it is. Strip away the myth, and the target gets very small. You are not looking for magical steel. You are looking for a process that works only when several ordinary things line up with absurd precision. Even that does not cover the whole loss. Modern decorative Damascus usually means pattern-welded steel. Separate layers stacked, twisted, forged together, then etched to reveal lines. It can be beautiful, it can be excellent steel, but museum language stays careful for a reason. Pattern welding and historical crucible Damascus are not the same process, even when the surface fools your eye. One builds the pattern by layering metals. The other draws it out of the internal structure of a single high-carbon crucible steel. So yes, a modern blade can look right. Looking right is the easy part. The hard part is recovering the network behind it. The ore source may have needed a particular trace element profile. The ingot makers had to know how to smelt and cast without ruining the carbon content. Traders had to move those cakes intact across long distances. Swordsmiths had to recognize which ingots were worth forging and how far they could push them before the watered pattern vanished forever. None of that lives in one formula scratched onto a workshop wall. It lives in a supply chain, and supply chains die piece by piece. A mine shifts, a trade route breaks, a patron disappears. An apprentice learns the shape of the blade, but not the temperature in the master's hands. Verhoeven's team proposed that the best historical patterns may have depended on a geological accident as much as on human skill. The right ore, carrying the right trace elements, no longer available from the original source. That may be true. It is still a theory, not a final verdict. The other possibility is less dramatic and somehow sadder. The materials may have survived. The social chain did not. The official version says the mystery was solved when modern researchers made museum-quality blades. The narrower, more unsettling version is this. They showed the pattern was not magic. They did not bring back the vanished world that once made that pattern routine. Recreating the look is an achievement. Recreating the original metallurgical chain is something else entirely. Number 3. The concrete that heals under the sea. The concrete that got stronger from the thing meant to kill it. In 37 BC, on the black water of Pozzuoli Bay near Naples, Roman engineers dropped massive harbor blocks into seawater and expected them to sit there and harden into a breakwater. They mixed volcanic ash, lime, volcanic rock, and water into a marine concrete built for piers and moles, the kind of structure that should have spent its life fighting the sea, not borrowing from it. But the sea did not simply attack this material. It entered the chemistry. For the next 2,000 years, that was the problem. The harbor still stood, not intact in the way a museum object is intact, but alive in the way stone is not supposed to be alive. When the Romacons project drilled into those Roman remains between 2002 and 2009, the cores went to Berkeley Lab, where synchrotron analysis found a binder unlike ordinary modern cement. Inside the matrix was a dense aluminum-rich CaSH structure, and inside the pores were rare crystals of aluminous tobermorite and philipsite, grown into the pumice and voids like a slow mineral frost. The concrete had not just survived seawater, it had recruited it. The first shock is simple. A block submerged in seawater is supposed to rot, soften, and crack apart under repeated assault. Roman marine concrete did something else, and for a long time, nobody could quite say why. The old assumption was simple enough. The ash and lime were durable, so the structure lasted. But that explanation collapses under the numbers. Modern ordinary Portland cement can show serious seawater degradation within 32 weeks in comparative work, while these Roman harbor blocks sat in aggressive marine conditions for roughly 2,000 years. That is not a small difference. That is a different physical outcome. The second twist came from the white specks people once dismissed as bad mixing. Those pale lime clasts looked for years like evidence that Roman builders had been sloppy. In 2023, MIT's work made them look deliberate instead. The idea was that the Romans may have hot-mixed quicklime into the concrete, leaving lime-rich fragments that could fracture under stress, dissolve when cracks opened, and then refill the damage. Not a flaw, a reserve. Not waste, a repair system built into the block itself. And if that sounds too neat, the numbers push back just enough to keep it honest. A highlighted review on January 24, 2023, framed Roman concrete as self-healing, but the exact recipe is still not pinned down site by site. Some mixes may have been made hotter than we once thought, with local temperatures above 200 degrees Celsius during preparation. Some may have depended on specific volcanic inputs. Some may have been tuned for harbor work and nothing else. The mechanism is becoming clearer, but the builder's decisions are not all sitting on the table in a single surviving manual. You can stand there in your mind, on the edge of that bay, and watch a block go under. Salt water presses into every pore, cracks open. Then the chemistry starts moving the other way. Pumice, ash, lime, and seawater stop behaving like separate ingredients and start behaving like a system. New minerals grow where the damage is. The 11 angstrom aluminous tobermorite, the philipsite, the calcium-rich phases inside the pores, they do the work that ordinary stone would never do for itself. The structure does not stay perfect. It keeps repairing the places where it fails. And that is what makes the harbor so unsettling. We are not looking at a lost miracle with no explanation. We are looking at a real engineering choice that turned marine destruction into mineral growth. But the exact proportions, the heating method, the way different Roman sites varied the mix, those are still partly out of reach. The concrete heals. The recipe still does not fully speak. The harbor keeps its silence, and the cores keep showing the same strange thing in the dark, cracks filled with stone. Number 2. The naval weapon water could not stop. On the edge of the Byzantine world, a refugee arrived in Constantinople with a problem that would become an empire's obsession. His name was Callinicos of Heliopolis, a Syrian architect who came north in the late 660s after the Arab advance through the Levant. The court did not just give him shelter, it put his knowledge to work. From that moment, Byzantine history began to smell like pitch, smoke, and panic. The first report that matters comes from the sea. Theophanes places the great test on September 1st, when Suleiman appeared with a fleet of 1,800 ships and anchored off Constantinople. The numbers alone are enough to tighten the throat, a wall of hulls, a city pinned to the water. Then the wind shifted, the Arabs were pushed outward, and the emperor launched fire ships from the Acropolis. Some enemy vessels burned against the seawalls, others sank with all hands. Water was all around them. It did not help. What kind of substance keeps burning with the sea right there? The sources never give us a neat laboratory label. They give us effects. They give us terror. They give us a weapon that spread so quickly by reputation that later writers treated it almost like a state religion. By the 10th century, Constantine VII was telling his son Romanos II that an angel had revealed the secret to Constantine the Great, and that it must never leave Christian Constantinople. Hidden, guarded, enforced, treated as something that could not be separated from the empire that used it. The power was never only in the burning liquid. It was in the delivery, the crews, the pressure, the siphons, the tanks. The people trusted to handle it without ever writing it down. Greek fire gets harder to explain the closer you look. The weapon's best defense was forgetting. If you only had the substance, you still did not have the weapon. If you only had the weapon, you still might not have the substance. The Byzantines appear to have protected an entire industrial craft, not a single magical recipe. The mystery is not only what it was made of, it is how it was made to work at sea. A formula in isolation is one thing. A flame thrown from a ship in a storm is something else entirely. By the time Greek fire was used on a large scale again in the great victories of 678 and later in 717 to 718, it had already become part weapon, part warning. Spring fleets carried grain, arms, and provisions. One fleet is said to have had 400 grain-carrying galleys and dromons. Another from Africa had 360 galleys loaded with arms and supplies. These were not just targets, they were floating lifelines. When fire reached them, it did more than kill men and burn wood. It broke supply, morale, and momentum at once. That is the kind of violence that changes how an army thinks about the sea itself. The exact composition stays out of reach. Proposed ingredients drift through the centuries. Petroleum products, resins, sulfur, quicklime, other mixtures. Each one explains a slice of the reports. None of them explains all of them. Some account for adhesion, some for ignition, some for the way the fire seems to have clung and spread. Battlefield descriptions also demand a delivery system that could project the substance under pressure, into chaos, across distance, while keeping the operators alive long enough to fire again. A bare recipe does not solve that, nor does a machine without the right fuel. The story only works when chemistry, engineering, and secrecy all line up at once. A modern replica built in 2006 was said to throw flames 10 to 15 meters, and even that is only a shadow of what the chronicles describe. Greek fire terrified because ordinary water could not put it out, and no proposed formula reproduces every account, every delivery method, and every layer of silence the Byzantines wrapped around it. The fire survives in the records as a weapon that should not have worked the way it did. The more carefully you examine the battlefield, the more it looks like the secret was not one thing at all, but a system nobody has ever fully recovered. Number 1. The computer at the bottom of the sea. The story does not move from fire at sea to fire in a laboratory. It moves from secrecy to subtraction, from a weapon hidden by necessity to a machine hidden by accident. When something survives only as fragments, the first question is not what it was called. It is what kind of mind could have built it at all. In the winter salvage season of 1900, Captain Dimitris Kontos and a crew of sponge divers from Simi were working a Roman-era wreck off the island of Antikythera. They hauled up statues, glass, coins, and one ugly corroded lump that looked less valuable than the art around it. Its shape made it easy to set aside, easy to kick aside, easy to forget. Inside that lump was the ancient machine that makes the rest of the list stand trial. The wreck itself is usually dated to around 70 to 50 BCE. The device inside the corroded mass was probably built earlier, around 150 to 100 BCE. By the time it reached the sea floor, it was already old. Not antique in the decorative sense. Old in the dangerous sense, where a piece of technology has outlived the culture that knew how to make it. On May 17, 1902, in the National Archaeological Museum in Athens, Archaeologist Valerio Staes noticed gear teeth inside one fragment. That single observation changed the object from shipwreck debris into a scientific crime scene. The rust was not just rust anymore. The corrosion was covering precision. For decades, researchers could see only broken bronze and a few exposed wheels. The fragments looked like the aftermath of something more elaborate, but the full shape stayed buried inside the damage. There were 82 surviving fragments, and among them about 30 bronze gears are documented today, with fragment A carrying most of the surviving mechanism. Even the size is unsettling in its restraint. The case may have been only about 33 by 18 by 10 centimeters, roughly a small wooden box. A machine that compact should not have been able to hold this much sky. Then the inscriptions started to matter. They were not decoration. They worked like an operating manual, naming displays, cycles, and celestial relationships that helped researchers reconstruct missing parts. Later imaging made the object speak more clearly. In 2005, microfocus X-ray CT and surface scanning revealed hidden gears and hidden text. What emerged was not a mystical relic, but a hand-operated astronomical computer. It could model the sun and moon. It could track eclipses. It could follow calendars. It probably modeled the 5 planets known in antiquity as well. On the back, one spiral dial mapped the 19-year Metonic cycle. Another followed 223 lunar months, the Saros cycle used for eclipse prediction. This was not a lucky charm with symbols scratched on it. It was a calculation engine in bronze. Once you accept what the device did, the mystery gets sharper, not smaller. No one is struggling to explain away a trick object. The hard part is explaining the technological lineage that produced this level of gearing so early, then left almost no direct descendants behind for roughly a millennium. The machine exists, the evidence exists, the inscriptions exist, the gears exist. What is missing is the workshop world that made such precision feel normal. Somewhere before the wreck, someone cut those teeth. Someone calculated the ratios. Someone assembled the gears so compactly that astronomy could fit in a box held in the hands. That implies tools, training, and a school of makers capable of turning mathematical theory into bronze motion. It implies a tradition of astronomical engineering that history only recovered by accident, piece by piece, from seawater and corrosion. And the details keep tightening. Recent work has argued that the front calendar ring may have held 354 or 355 holes, suggesting a lunar year system rather than the older 365-day assumption. That means the machine was not just counting time in a vague way. It was making a choice about time. It was encoding a model of the heavens into physical parts, with every hole, mark, and gear ratio tied to a specific logic. So the object does not leave us with a legend to believe. It leaves us with a problem to solve, not alien hands. Not a lost myth, a lost engineering culture. The strongest evidence is the least glamorous one. Bronze gears, inscriptions, astronomical cycles, and mechanical choices that prove ancient expertise without needing fantasy to prop it up. The Antikythera Mechanism was not a miracle. It was the surviving edge of a science we can still see, but can no longer fully trace.